right, so in this particular problem, we have two blocks. We have M1, and then we have M2 that's resting at the bottom of this horizontal surface. It says here the initial height is 2 meters, and then it says M1 is twice the mass of M2, where I'm circling back and forth with my cursor here in the statement. And it says the coefficient of kinetic friction for this rough horizontal surface is 0.5. All right, other than that, I'm just going to go ahead and get going with part A, B, C, and D. If you need to, pause it, read it for yourself. Part A wants you to find the speed of block 1 just before it strikes block 2. So this block 1 is going to slide down this frictionless ramp, curve, whatever you want to call it, and then it's going to attain some speed. So what is that speed at the bottom? So I'm just going to go ahead and set up conservation energy here. I have MEI equals MEF, or mechanical energy initial of the system equals mechanical energy of the system in the final frame. And then I'm just going to break up MEI and MEF. So ME is just composed of PE and KE for this particular problem. There's no spring involved here. And on the right side, likewise, MEF can be broken up to PF plus KF. However, I want to cancel out KI because it starts at 0, so it does not exist. And then PF for block 1 as it comes down to this horizontal segment. Therefore, there's no height. So we can just cancel that out. Okay, so I'm just going to break up PI equals MGH, and then KE is just 1/2 MV squared. But you notice here we're looking at M1, so I have a subscript M1 on both sides, but M1 is going to cancel anyways. So to get V1F squared by itself, I have to multiply both sides by 2. So I'm going to go ahead and move this 2 in the denominator to the bottom, excuse me, to the top left. And keep in mind this is V1F squared. So therefore, to get V1F by itself, you got to square root both sides. So here, we know G, we know H being 2 because it was given in the statement. And then other than that, we just go ahead and plug values in and then just square root that, and you'll get 6.26 meters per second. Okay, so and because they asked for speed, I don't need to give a direction. So the speed for block 1 at the bottom of the ramp is 6.26, and that's the answer for part A. Let's do part B. Part B wants you to find what is the speed of block 2 after collision. So here I have in the diagram here, I move M1 down to here because now we know that it's moving, and it's moving at a rate of 6.26 meters per second just before it strikes M2. Okay, so so therefore we just go ahead and do this part B and C on this one. So to do part B, all we have to do is set up conservation linear momentum. That's because they are going to collide, and once they collide, the blocks will have different speeds as they move. Okay, so I'm just going to set up a conservation linear momentum initial equals conservation linear momentum in the final frame. I want to break it up into two terms. There's P1I plus P2I, which equals P1F plus P2F. However, I want to cross out P2I because it's just the block 2 was initially at rest before it got struck by M1 as it comes down the ramp. All right. So I'm just going to break up the left side because it's P1I. I'm just going to write M1 V1I, and then likewise on the right side, I want to write M1 V1F plus M2 V2F. However, what I did highlight here is M1. Okay, and this is important. I like to use the strategy. The problem itself says that M1 is 2 times M2. So I don't know what M1 is. I just know whatever it is. Oh, the actual value, but whatever it is just twice of M2. So I'm just going to go ahead and replace M1 with the statement that was given to me in the problem. So M1 can be substituted for 2M2. And that's the only difference here in the third line and the fourth line. Okay, so the two M1s that are highlighted, I just replace it with 2M1 because that's what it is. And other than that, if you are looking at it, there's an M2 in every term, so I'm just going to cross that out. So I'm just going to simplify this real quick. 2 times V1I, but what is V1I? Well, we already found V1I. Okay, so before the collision, the block is moving at a rate of 6.26, which we calculate in part A. So if you take 2 times 6.26, you'll get 12.52. And then on the right side here, this is V just 1F, excuse me, 2 V1F. I don't know what V1F is, so I'll have to keep it as is. And then this M2 already cancel out, so it's just V2F in this term. So as you can see here, we have a statement with two unknowns. So we do have to get a little clever and unlock this problem. Okay. All right. So the next thing I want to do is I realize this problem is elastic. So I highlight in blue here. So when they collide, they're actually not sticking together. They'll bounce off but it says elastics. So I know that conservation of or the kinetic energy of the system has to be conserved. So I'll just go ahead and set up kinetic energy here in order to unlock this particular problem. All right. KEI of the system must equal to KEF of the system. But initially, you have just one block moving, and that is block 1 at the bottom of the ramp. So here on the left side, I just put 1/2 m1 v1I square. It's m1 only because block 2 was not moving before the collision. On the right side though, however, I have two terms. I have 1/2 m1 v1f square plus 1/2 m2 v2f square. So as you can see here, there's a 1/2 in every single term, so I'm just going to cross that out. And then in addition to that, just like on the left side, there's an m1 and an m1 here that I highlight in yellow. I'm just going to substitute it out for 2m2, okay? And then v1i is 6.26 that we calculated in part A. And on the right side here for m1 that's highlighted in yellow, I also substitute it out for 2m2. And then I just carry everything down that I haven't gotten rid of, all right? So you need to notice here m2 cancels out as well because now the whole statement is in terms of just m2, right? So you can cancel it out. If you do your calculator work correctly, if you do 6.26 square times 2, you'll get about 78.38. And then on this side here, there's really nothing I can do in terms of calculator work because you have two unknowns. So here I'm just going to carry the 2 that I haven't canceled out yet, and then v1f squared just get carried down. Excuse me, I can't speak right now. And then v2f squared just gets carried down as well. So as you can see, you have two unknowns, which kind of matches with what we have on the left side here in my work using conservation of linear momentum. However, this is v1f by itself versus v1f squared. This is v2f versus v2f squared. So pay attention to the details there before you make any false math substitution. Okay. All right. But now I need to get rid of one of these either v1f or v2f here. I have v2f squared already kind of by itself. There's no coefficient in the front. So I think it's easier to just move this 2v1f squared to the left side. So it's positive, so I'm just going to go ahead and subtract it from both sides. So here I have 78.38 minus 2 times v1f squared, which is equal to v2f squared. Okay, but this is v2f squared, as I stated, so you have to get v2f squared on this side as well. Well, how do you do that? Just go ahead and get v2f by itself first. So to get v2f using conservation of linear momentum here, you need to move this 2v1f to the left side, which changes sign. So instead of positive, it'll become negative. So it'll be 12.25 minus 2 times v1f, which equals to v2f. But once again, this is just v2f. It's not v2f squared yet. Well, to get the v2f squared, you got to square both sides of the function. So, but what you do on one side, you got to do the other. So don't forget to do this properly, okay? Here, this is 12.52 minus 2 v1f, but I'm going to square it. So I'm going to write it out twice in parentheses. So it's going to get multiplied by itself, okay? So here you have to do FOIL. And if you do FOIL correctly, you should get 156.75 minus 50.08 v1f plus 4 v1f squared, okay? So if you take 12.52 times 12.52, you'll get 156.75. But then both of these signs in the FOIL are negative. So really, all you have to do is just take 12.52 times it by negative 2 v1f, and then times it by 2 again because you have two identical terms. So that'll give you 50.08. And then the negative 2 v1f times negative 2 v1f. So negative 2 times negative 2 makes positive 4. And then v1f times itself is v1f squared. And then that is v2f squared if you do FOIL correctly. All right. So now that you have two statements, I'm just going to go ahead and set these two functions equal to each other. So I'm just going to carry my work up here. So you have two statements for v2f squared. So set them equal, and then just go ahead and solve it. Okay. So here, I just carry my work up. 156.75 minus 50.08 v1f plus 4 v1f squared equals 78.38 minus 2 v1f squared. And then I'm just going to go ahead and combine like terms. So listen here. Here's the 78.38. That doesn't have a v1f, so I'm just going to combine it with the 156.75. Those are like terms. So this is a positive 78.38, so I'm going to move it to the left side, which causes it to be subtract. So if you take 156.75 minus 78.38, you'll get 78.36. And then this right here is negative 2 v1f squared. So when you move this negative term to the left side, it'll become positive. So therefore, I can add it to this 4 v1f squared, right? This is a negative 2 v1f squared, which is combined with this like term here, because this term is a positive 4 v1f squared. So that'll make it 6, and that's where the 6 comes from. So here I just wrote it from highest the lowest exponent, because you do need to use quadratic to solve this. So you notice I set the whole function equal to 0. I only combine like terms, and then that's it. So here, if you use your quadratic, your a constant will be 6, and then your b needs to be negative 50.08. So don't forget that negative sign. And then your c, which is a term by itself with no variable, is just 78.36. It's positive, so I don't have to worry about that part. Okay. So if you do this correctly on your calculator, you'll get a value of either 6.26 or 2.09. Okay. Now, the answer cannot be 6.26 because the speed of block 1 at the bottom of the ramp before it struck M2 is already 6.26. After it collides, it has to be a different speed. It has to be some value lower. Okay. So in this case, even though you get two answers using quadratic, I would go with the 2.09 because that's the only one that makes any sense. Okay. After you struck something, you can't be moving with the same speed. That's just kind of weird. All right. So that is V1F. Okay. However, part B asks for the speed of block 2. So I'm not done yet. Now that I have V1F, I can just really do this. Right. Earlier, in using conservation momentum, I have a statement for V2F by itself. Well, I just found V1F, so I can just use the statement and plug in values. So it'll be 12.52 minus 2, but I just found V1F to be a positive 2.09, so I'm just going to substitute that in. And if you do your calculator work, 2 times 2.09 will give you 4.18, and then 12.52 minus 4.18 will give you a value of 8.34. And because part B asked for speed, I left the answer just in its magnitude form without the direction. So the speed would be 8.34 after the collision. Okay. And then part C here asks you to find the velocity of block 1 immediately after collision. So as a matter of fact, I already have this answer because using the strategy that I have, I actually already found the speed of V1F after the collision. So again, once you do quadratic, you have two answers. I'm going to go with the one that makes sense, which is positive 2.09. So part C is done. Okay. All right. Let's go on and do part D. Part D asks you to find the distance that M2 will travel before coming to a stop. So I'll do this a couple of strategies for you quickly here. One, we know that M2 is going to go off after collision at a rate of 8.34 meters per second because that's what we just calculated in the previous part. And then here, you can just do work kinetic energy theorem. The net work on block 2 is the change in kinetic energy for that particular block. So you notice here every subscript has a 2 in it. So make sure you focus on the mass that you're asked to assess. Okay. So net work equals change kinetic energy, which is KEF minus KEI. Here I'm going to cross out KEF because it comes to a stop. Well, therefore, the net work done on it is simply the work due to friction. So as M2 slides across this rough surface, there's only one horizontal force acting on it, and that is F of K pointing leftward. So if the block is going to slide rightward, F of K is acting against the motion, which will point left. And it is the only force. There's no applied force here. So therefore, I can define work as force times displacement. Here I just wrote my displacement as D because the problem, the statement here uses the letter D. It doesn't really matter because it's moving one way, so the displacement and the distance would be the same magnitude. Okay. All right. And then on the right side, I'm just going to break it up into 1/2 M2 V2I squared. And I'm just going to carry that negative sign down. Therefore, all you have to do is just substitute out FK. FK is mu K F of N. But this is a flat horizontal surface and there's no additional funky forces, I say. So therefore, F of N is just equal to F of G, or the magnitude of F of N is equal to F of G. All right. So I can just go ahead and get rid of F of N by saying that F of N is the same as the magnitude of F of G, and F of G is just M times G, but it's M2 because we're looking at block 2. And the right side stays the same because nothing has been substituted out, and then M2 cancels out. So here, as you see, you have mu K, which is given as 0.5 in the problem. G here is 9.8, and then D, well, that's what we're trying to find. So keep it as is. And then on the right side, V2I square. Well, we know what V2I is. Block 2 is going to move into this region with the speed of 8.34. Therefore, all you have to do is do a little algebra manipulation. So to get D by itself, divide both sides by mu K and G. So I'm just going to move the mu K and the G down to the denominator. It's going to join this 2 that's already on the bottom. All right, so now we have all the values. Plug it in. VI, once again, is 8.34. I want to square that. and then 2 gets carried over, mu k is 0.5, and then g here is negative 9.8. And then if you do this correctly, the signs will cancel out, and it will tell you that the distance here is 7.1 meters. So since it asks for distance, I don't have to worry about the direction because distance is a scalar, so that's it, 7.1 meters. That's how far it will travel before it comes to stop. If you don't like this work kinetic energy theorem, you can just use your old school kinematics and Newton's second law. So here, this is kinematics function, Vf squared minus Vi squared equals 2a delta x, but delta x here I just wrote as d because once again, it's just moving to the right. Here, Vf gets crossed out because it comes to a stop. But what I don't have is that I don't have a. To get d by itself, just divide both sides by 2a. But I know v2i is 8.34. The 2 is just given as part of the function here. I don't know what a is, but because I don't know what a is, I need to set up Newton's second law. As it slides across this rough surface, the net force along the horizontal direction is simply only f of k. So we can just say f of k is causing the system to decelerate. So therefore f k equals ma. And then you can break up fk once again into mu k fn. But as I stated earlier, using the work kinetic energy theorem, the block here, watch my cursor, right? It's making contact with the surface, so Fn is going to push up. But at the same time, the weight of the box is keeping it down. But the net force in the y direction is 0, so it implies that the magnitude of f of n must equal to the magnitude of f of g. So we can substitute out f of n for f of g. But f of g, but once again, by definition, is just mass times gravity, which mass 2, because that's what one we're looking at. And then m's will cancel out. So the acceleration is simply 0.5 times negative 9.8. And the acceleration in this case has to be negative because it's acting against block 2's motion. So block 2 is sliding rightward, it's decelerating, so a has to be pointing in the opposite direction. So therefore, a here is negative 4.9. But now that you know a, you can just carry this statement down. So here, I'm just going to go ahead and plug values in. V2i is just 8.34 because that's what we calculated. And then here a we just found, which is negative 4.9. If you do that, you'll get the same answer. Okay. All right. As you can see, it doesn't really matter which strategy you apply, you'll get the same value. I do want to point out, in case you are not keeping up here, if you look at the statement that I'm circling back and forth right here, right? In the numerator, you have negative v2i squared divided by 2a. I plug in all this calculator work for you if you really like calculator work. However, if you pay close attention, in the statement here using Newton's second law, we have a statement that says A is mu k times g because the mass can't already cancel out. So if I just substitute A out for mu k times g because that's what it equals to, so you have vi squared divided by 2 mu k g. But if you look at my cursor on the left side here, to solve for d, we already have the statement using the work kinetic energy theorem. We have v2i squared divided by 2 mu k times g. So as you can see, because the function is the same, it will give us the same answer. Okay? All right, stay nerdy, don't be whack.